Welcome back, everyone. We started the day with amazing talks by Dr. Ross King and Dr. Abhishek Singh, where they explained how AI can help in automated discoveries. And we went on a break asking a question: should AI also be giving the exams, right? So our next speaker will be talking about on a similar topic, where they have experimented on AI giving and clearing grade 8 exams. So welcome our next speaker, Dr. Peter Clarke, who is a senior research manager at Allen Institute of AI and leads the Aristo project. His work focuses mainly on natural language processing. And Am I audible? Reasoning and world of knowledge. And so he could not join us in person because of the time zone difference. We'll be playing a pre-recorded message, a pre-recorded talk by him.
Hi, I'm Peter Clarke. I'm at the Allen Institute to tell you about Project Aristo. It's a system we've been working on for several years that attempts to answer science questions and perform scientific reasoning. So it's a fascinating question asking, can a machine win a Nobel Prize? But let me back up one step and ask a more basic question, namely, can a machine even pass a basic science exam? So science exams themselves are pretty complex, requiring many skills in reasoning. For example, here's a question from an 8th grade science exam. So this is an exam that a 13 or a 14-year-old would be expected to take. And the question reads, how are the particles in a block of iron affected when the block is melted? And the correct answer is the particles move more rapidly. And the reason this is challenging is because it requires both physics knowledge, namely if something is at high temperature, then the particles will move more rapidly, and also common sense knowledge, namely if something is melted, then it'll be at a high temperature. And so at AI2, we've been working over the last 5 years on a system called Aristo, which has been aiming to give machines some basic knowledge and understanding of science. And the way we've been testing Aristo is to test it on real science exams, which are given to kids. So what I'm going to do in this talk is just describe Aristo, the progress we've made, and some of the insights that we've learned in that endeavor. So when we started back in 2014, we measured Aristo's progress on a bunch of different tests, but here I'm going to plot its performance on non-diagram multiple choice questions, which are the type of questions we've been targeting the most. And when we started, Aristo originally scored about 36%. The next couple of years, we added in some information retrieval methods and some rule-based reasoning methods to help Aristo perform better, and its scores went up to about 63%. And then at that point, we threw the challenge open to the general public, and we launched the Allen AI Science Challenge. We made our data available, and we challenged the community to see if they could build a system that could ace this exam. So this competition was pretty successful. We had about 3,000 people register. We had 750 teams enter the competition. But even after all that work, the best system barely scored above 60%. And that led, in turn, to the following article, which appeared in the business magazine, saying the best AI still flunks 8th grade science. And this result kind of reflects the challenges which science exams pose. We continue to work on Aristo. We added in new methods using statistics and additional reasoning methods. And then the most dramatic change has happened in the last 2 years when we added in new techniques using so-called language models or neural net techniques, which made a dramatic difference to Aristo's scores. In fact, we saw Aristo scores go up to over 90% using these new techniques. In addition to testing on our test suites here, we also tested Aristo on the latest 3 exams that were issued since our project started. These are exams between 2017 and 2019. And again, Aristo scores over 90% on these multiple choice questions. So this isn't just a fluke, it's reflects a significant advance in the field of language processing and machine understanding. So this result received a fair amount of publicity. It made headlines in the New York Times and also in a number of other news outlets. And so what I want to do in this talk is to have a look inside Aristo, talk about what it's doing and what it can't do, and the extent to which it has some understanding of science as a first step towards a machine that can make discoveries and maybe ultimately win a Nobel Prize. So first, how does Aristo work? So at a very high level, Aristo contains a number of different solvers that independently try to answer a question, and then there is a combiner module that ensembles the different conclusions that the solvers make together. I'm not going to talk through all the different solvers that are there. Rather, I'm going to just focus on one class of solvers called the language model solvers, which are the ones that we've added most recently and are the ones that do the heaviest lifting in terms of answering questions. So language models represent the latest development in neural techniques, and there's 3 interesting things about them. The first is they are extremely good learners. You can feed in a question and maybe some data and examples of the answers that you want it to produce, and they are very effective at learning the patterns involved in answering various questions. The second thing about them is very often it's not necessary to include a lot of structured information in the data that's provided. That is, we can provide questions and data in natural language, and these systems seem to learn very effectively without resorting to parse trees or various other linguistic techniques. And then the third thing, and perhaps the most significant thing, is the neural architectures don't come as a blank slate. Rather, they are, first of all, pre-trained by having them read vast amounts of text, for example, Wikipedia and a large collection of books. And these neural systems in this pre-training phase learn to predict what kind of words and phrases are likely to come next. And this pre-training seems to give them additional power in terms of learning patterns from the question and data that are supplied. So in the Aristo case, what we do is to answer a question, we supply it with a question and maybe one of the answer options. And then we also go out to a large text corpus that we've collected of science knowledge and retrieve about 20 to 30 sentences that seem relevant to the question based on the keywords inside it. And then from that, the system digests this and then produces an answer. So in this case, we ask what parts of a plant need sunlight to do its job. It comes out with the answer, the leaf. And we train Aristo using several thousand science questions in addition to several 100,000 general multiple choice questions in order to improve its performance. So I've given a fairly simple and high-level picture of what Aristo's doing. It's taking a question, it's finding some science knowledge, it's sort of reading that science knowledge and working out the answer to the question. But the real interesting issue is, well, what is going on inside the system? Does it really have an understanding of science, or is it just looking up the answer in the text that it's retrieved? So we've done a number of probes on Aristo to try and illuminate exactly what's going on inside, and I'll describe that now. So one of the most interesting questions is whether Aristo is simply looking up answers in text, or does it have a more detailed understanding of the domain it's talking about? And when we play around with Aristo, it seems to be doing some fairly clever things. One of my favorite illustrations of that is this question here. So it reads, city administrators can encourage energy conservation by doing what? Lowering parking fees, or decreasing the cost of gasoline, or lowering the cost of bus and subway fares? And in fact, the answer to this question is the last option, lowering the cost of bus and subway fares. So if you lower bus fares, there'll be more public ridership, there'll be less private transportation, so presumably energy will be conserved. So let me illustrate giving this to the Aristo system itself. So this is the Aristo system, and what I'm going to do is to scroll down to the bottom to the type-in box, and we're going to enter in the question I just described. City administrators can encourage energy conservation by doing what? We give the question to Aristo, and it comes up with the correct answer, lowering the cost of bus and subway fares, as expected. What's more interesting is if I go back and I re-ask this question, but I'm going to change lowering to raising, and I'm going to change decreasing the cost of gasoline to increasing the cost of gasoline. And then if I re-ask this question, Aristo correctly changes its answer. Now it says increasing the cost of gasoline will encourage energy conservation. Again, if I can go back, I can edit this again and say, let's, instead of encouraging, let's discourage energy conservation. We'll re-ask the question. And again, Aristo changes its mind and gets the correct answer, raising the cost of bus and subway fares. So what this is illustrating is something very interesting. So the system is not just matching the question against text that it's seen in the past. Rather, it's demonstrating some knowledge of these concepts like increasing and decreasing, raising and lowering. In other words, it's showing that the system has acquired some sort of semantic understanding of the language it's manipulating in the course of its training. Now, of course, what I've shown here is just anecdotal. Can we be more systematic to try and assess whether the system really has learned some of these semantic concepts? And that's what I'll show in the next slide. So we can think in terms of a kind of scorecard for Aristo to measure its understanding of various semantic phenomena or meanings that it's expected to be able to handle in order to do basic science. For example, negation, does it understand how to handle the word not? Conjunction, dealing with the word and, polarity, and so on. So to test these, we did a number of synthetic tests. So first of all, for negation, we gave Aristo a number of questions which looks a bit like this one shown here. So we give it some imaginary information about some people. So, Alan is small, Charlie is big, Bob is big, and so on. And then we ask a question like this one: which of the following is not tall? Alan, Bob, Charlie, or David? And here the correct answer is David. And when we give this question to Aristo, we find that even without any training on this type of question, it scores 94%, which is very surprising. It suggests that Aristo does have some systematic understanding of the word not, given lots of different questions like this. And I should emphasize this is without any training on questions like this. This is simply what it's learned from all the science questions it's observed in the past and the pre-training. So for this, we'll give it a grade A using the traditional rubric, kind of nice work. Secondly, for conjunction, so how can we test its understanding of the word and? So again, we can give synthetic questions. And they look like this. We'll give, again, some fictitious context, like Alan is big, Alan is red, and so on. And we'll ask a question, which of the following is big and blue? So testing its understanding of the word and. Here the correct answer is Charlie. And what we find is, just with one and in the question, it scores 98%. Even with 4 ands in the question, its scores still stay as high as 80%. And if we add in a negation, the scores still are up in the mid-70s, which is really quite amazing given the complexity of these questions. just to illustrate that, here's 4 conjuncts and a negation question. So again, we give some context as shown here, and then we're going to ask the following question: which of the following is old and red and light and big and not short? And again, the system is coming up with the right answer 76% of the time. Again, illustrating its ability to manipulate some of these logical connectives. And as I've emphasized, we didn't train the system on these particular types of question. This is just an immersion capability which has emerged from its training on lots of examples. So according to our rubric, we'll give this system a B+, as its scores are in the 80% to 98% range. And so I'll jump ahead. I won't show the other different semantic tasks, except to say Aristo shows evidence of understanding these different phenomena. The one it did bomb on was counting. So questions are like this one: Daniel picked up the football, Daniel dropped the football, Daniel got the milk. How many objects is Daniel holding? 0, 1, or 2. Aristo does terribly at this. It scored only 6%, and so we'll give it an F here. So it doesn't have any built-in knowledge about how to count things, although it does know some of these other phenomena. So the evidence from these initial probes is that Aristo is doing more than just looking up answers in text. Rather, it's able to take some science text that it's retrieved, be able to read it in some sense, and extract some of the meaning and enough to apply that knowledge in a fairly sophisticated way to the questions which it's being given. However, although Aristo's scoring 90%, that does mean it's getting 10% of the questions wrong. So we've also done some explorations to see where the system fails and what kind of questions tend to throw the system. So I'll describe those now. So we did a case study on 30 example failures of Aristo. We were particularly interested to know, when it got a question wrong, was it that it didn't retrieve the right knowledge that was appropriate for the question, or did it have the right knowledge and it just failed to really understand what the text was saying? What we found was only in 4% of the cases, 4 of the cases, had it retrieved good support for the correct answer, but still got the answer wrong. There was one case where it's actually retrieved good evidence for an incorrect answer, so arguably that's a failure of the design of the exam itself. The majority of cases, though, were questions where it was not able to find the right knowledge in its science repository, and so it was left floundering. And then, very interestingly, there were also 8 cases, about a quarter of the questions, which were not quite the traditional science questions you would expect, where information direct from a textbook wouldn't help answer those questions. So I'm just going to give some illustrations of each of these failure cases in turn. So first of all, examples where there was good support for the correct answer. So this is a somewhat subtle question which Aristo got wrong. Which is the best unit to measure distances between Earth and other solar systems in the universe? Miles, kilometers, light years, which is actually the correct answer, or astronomical units, which is the one it picked. And the reason it should have got the answer right is because in its retrieved information, it had the sentence, distances between Earth and the stars are often measured in terms of light years. But it was confused by also retrieving this information that says, in general, distances within the solar system are measured in astronomical units. So you can see here there's a subtle difference between distances within the solar system versus distances amongst different solar systems, and Aristo got confused and produced the wrong answer here. Admittedly, this is a somewhat confusing question. A human could be understood for also making a similar mistake. There was one example I mentioned where there was good support for the incorrect answer. So the question here was, which of these objects is most likely to float in water, a rubber ball or a tennis ball? In fact, there's lots of sentences that are retrieved saying rubber balls float, and hence it selected that rather than selecting the intended answer, which is tennis ball. Here, Aristo didn't really understand the notion of most likely, so it wasn't able to do comparisons amongst answer options, and so that led it to fail in this case. And then, as I mentioned, there are a number of questions which were less based on retrieving science knowledge. So one is story questions. So in this question, an experiment is described, and the question asks, what's the independent variable? The correct answer is the amount of garlic. It shows the amount of growth. And so retrieving information is not going to help in understanding this particular story. And then similarly, a kind of meta question, which statement is an opinion? And it gives various statements. Aristo picked plants require sunlight, whereas the correct answer is many plants are beautiful. Again, Aristo has no knowledge about what an opinion is from fact. So again, there's some information that's missing. And then finally, this is a particularly interesting error it made. About how long does it take for the moon to complete one revolution about the Earth? So the correct answer is 30 days. It's actually selected 365. And when we look at the information it read, it has statements like it takes the moon about 27.3 days to complete an orbit, 27.3 days, 29.5, and so on. But actually, the neural system has no understanding that 27.3 is very close to 30. And so because of its inability to do those approximate comparisons, it failed on this particular question. So far I've shown that new neural language models have enabled Aristo to be able to read science texts, extract some of the meaning in a fairly sophisticated way and apply it to new questions. But I've also shown that Aristo fails on a number of classes of questions. So what I want to do now is just point to several steps forward to go beyond its current capabilities to provide more sophisticated scientific reasoning. So the first big step forward is the use of new generative models. So you might have heard of GPT-3, and there are various other new, even more powerful language models, neural language models that have come along, which don't just classify answers, but can actually generate new text. And so the idea here is we can feed in a question like this one: what force pulls a ball down a hill? And the system can generate directly answers to the questions, like the answer gravity, and maybe you can also generate explanations like gravitational force causes objects that are mass to be pulled down on a planet. So this new capability is really quite impressive as well. It goes beyond simply multiple choice questions to doing this kind of generative creation of answers. And quite recently we've trained new models on large data sets of questions with answers and explanations. So let me just give a little illustration of one of our new systems answering a question. So I'm going to enter a question here. So plants do not usually need to eat other organisms because plants do what? And so I'm going to pose this question. And the system here has come up with an answer. So it said make their own food. It's also synthesized an explanation here. So a producer is a source of energy for consumers. In the food chain process, an animal has the role of consumers, which eat the other animals for food, and so on. So these sentences here provide some justification for the answer which is produced here. And it's important to note these explanations are not retrieved sentences. These are synthesized by the system based on its previous knowledge of science. So this is one of the first important steps forward to take systems beyond classification tasks to generative tasks. And this illustrates that new language models are acquiring that capability fairly rapidly. A second requirement for more advanced question answering is the ability of a system to decompose questions. So in this particular example, we asked Aristo what virus structure is similar in function to a cell membrane. So this is quite a complex question, and without breaking it up, the kind of information that the system pulls back from its science corpus is a rather motley collection of text, which doesn't really provide the information that's required. Instead, what we'd prefer is for the system to be able to decompose this question into more modular units. For example, first we'd like the system to say, well, to answer this question, we want to know what's the function of a cell membrane. Maybe the system realizes it's to surround and protect. Now we can ask what part of the virus surrounds and protects, and now we'll get back the right answer, the protein shell. So this ability to break complex questions into structured decompositions is something Aristo doesn't do at the moment. It's an area we're working hard on at the moment. A third and important requirement is for reasoning systems to be able to model the different states of the world, and in particular world dynamics. So for instance, given a paragraph describing a process like this one about photosynthesis, when you or I read this, we create a mental picture of the world and how it changes throughout the paragraph. For instance, we read roots absorb water from the soil, and we imagine, okay, there's some water. It was in the soil, now it's at the roots. And then we read the water flows to the leaf, and we create a picture of the water now flowing up to the leaf. And as we read through, we create this mental envisionment of the world and how it's changing. Now, neural systems, including Aristo, are currently very bad at doing this. They don't even realize that a changing world is being described here. And as a result, when we ask questions like, where is the sugar created? It seems fairly obvious to a person. It's created at the leaf, because that's where all the components are going to. Neural systems fail badly. So, for instance, they might produce this wrong answer, light, water, CO2, which is not even close. So we've done some recent work on trying to train the system to model world states by creating a simple representation of the world states at each step within a process. So this system takes an action, like the first sentence here, roots absorb water from the soil, and it makes a note in its table that the water was at the soil and has now moved to the roots. You can think of it as creating at each stage a little picture of the world. So here we have the world with the water and the soil, then it's moved to the roots. Similarly, then the water flows to the leaf. So now we note that the water moves from the roots to the leaf. And again, this little mental simulation of the world state increments forward. And we can repeat this to the end of the process and have the system create a sequence of states like this in order to envision how the world is changing. So this is a pretty fundamental capability that people have that seems to be essential for scientific reasoning, particularly about world dynamics. This is something that doesn't come naturally to neural systems, but with a layer on top, as we're trying to do here, it seems to be possible to at least emulate to a certain degree. And finally, one really important requirement is to have neural systems do some kind of systematic reasoning, particularly if we want to be able to interact with the system and have it understand and react to what we say. So what I've shown you so far is neural systems doing clever things, but in somewhat of an opaque way, and that is kind of a barrier both for understanding what's going on inside and for correcting a system when it seems to be going wrong. So for instance, we'd like a dialogue like this. We'd like to be able to ask Aristo, can you pick up a penny with a magnet? Maybe it says yes. I might ask why, and it'll give me an explanation like pennies are made of metal, metals are magnetic. And then if I disagree with that answer, I'd like to be able to argue back and say, well, actually that's not the case. Not all metals are magnetic. For instance, copper is not magnetic. Try again. And then the system tries again and says, well, now I think the answer is no, because pennies are made of copper and copper is not magnetic. So in order to support this kind of capability, it's essential that the system is not just putting knowledge together in a rather opaque way, but it's actually following basic rules of reasoning. So one of the most exciting works we've been involved in this year is trying to teach neural systems not just to answer questions, but to also reason in a systematic way itself. So how can we do this? Well, we can train it. So we might give it a training example like this one. Metals are magnetic, nails are made of metal. Is it true that nails are magnetic? And we want the system to produce the answer true. Similarly, if we gave a different set of inputs, so say we give a counterfactual example, metals are not magnetic, nails are made of metal, is it true that nails are magnetic? So again, based purely on the data I've given it, in this case, it should answer false. So if we give examples of systematic reasoning like this? Can we train a neural system itself to perform this kind of systematic reasoning? And it turns out the answer is yes, and we built a system called RuleTaker, which is another step towards having systems perform systematic reasoning towards for science purposes. So let me just again give a quick illustration of this. So here I'm going to enter a set of facts and rules into the RuleTaker system and see whether it's able to reason systematically with what I've given it. So I'm going to tell it metals conduct electricity, insulators do not conduct electricity, nails are made of iron, iron is a metal, and then based on this I'm going to ask, well, is it true that nails conduct electricity? And if I submit this to the RuleTaker system, it comes up with the correct answer, which is true. If I now give a counterfactual world in which we say, let's say iron is an insulator, and we ask, do nails conduct electricity? Now it correctly says false. So reasoning about this counterfactual world. Similarly, if I say, let's imagine nails are made of plastic, and plastic is an insulator, and then we ask, do nails conduct electricity? Again, it correctly says false. And again, let's imagine a counterfactual world where plastic is actually a metal. And now if we ask, do nails conduct electricity, it comes up with the answer true. So this illustrates neural systems reasoning systematically with the facts and rules they're given. And this is an essential requirement if we're to understand what they're doing and also be able to argue back and correct their mistakes. And so this is a really exciting new line of work that we're involved in, which we're pushing hard on. So let me summarize and just give some reflections. So we've had surprising success with the modern neural techniques. If you'd asked me 2 years ago, could an AI system pass 8th grade multiple choice? I wouldn't have believed it. If you'd asked me a year ago, could a neural system produce direct answers and high quality explanations? I wouldn't have believed it. So neural nets have shown some ability to read scientific text and apply it to science knowledge and to science problems in a systematic way. But at the same time, they are limited. They're great at imitating. They're not so good at reasoning in a systematic way. And as I showed, they fall short on numerous types of questions. So I think, in the quest for scientific reasoning and ultimately scientific discovery, there's still a long way to go. The good news is that neural systems are an entirely new toolkit for AI. I think of them as the great imitators. They can be trained in a myriad of ways. As I've hinted at earlier, I think what we need going forward is to reintroduce kind of systematic reasoning in our modern systems, but maybe using language-like representations rather than the traditional formal representations. It's going to be most exciting to see how the future develops. So thank you for your time. I hope you enjoyed this, and I wish you luck with the rest of the symposium. Thanks a lot.